Welcome to Visual Algebra Lecture 2.1, Complex Numbers and Matrices. Let me first take a few steps back and say some words about the bigger picture. Chapter 2 on examples of groups is, I think, the longest chapter in my book, and therefore it will be the longest section in this video series. Fundamental to a large number of the groups that we will see are complex numbers and matrices. And this introductory lecture is to review that and put in context a lot of material going forward, especially involving rotations and roots of unity. Okay, let's get started. In the previous chapter, we encountered groups meant to appeal to intuition and motivate key concepts. Most of these involved symmetries or puzzles, like operations or configurations on certain states. In this chapter, we'll introduce a number of families of groups, some of them standard, some of them non-standard. I can't emphasize this enough. We will need a diverse collection of go-to examples throughout the course to keep us grounded and motivate key concepts. We'll begin with 4 standard families of groups that you'll learn about in any introductory course or textbook. First, cyclic groups. You can think of these as groups of rotational symmetries. So things like the symmetry group of pinwheels. Next, abelian groups. This is any group where multiplication commutes. So AB is always equal to BA. This is a larger class than the cyclic groups. Next, we'll see the dihedral groups. These are groups involving rotational and reflective symmetries. These are the symmetry groups of n-gons. We've seen some of these before. I talked about the symmetry group of the equilateral triangle, the square, and the hexagon in the previous section. Next, we'll look at permutation groups. These are groups involving collections of rearrangements. We'll show that every finite group is isomorphic to some permutation group. Then, by modifying some of our familiar groups, we'll encounter 3 lesser-known families. First, we'll see the quaternion groups and the dicyclic groups. Now, we saw the standard quaternion group on 8 elements in the previous section. There's actually an entire family of these called generalized quaternions. And there's even a larger family called the dicyclic groups. This is a very natural construction from the standard quaternion groups that most people don't actually know about. Next are the diquaternion groups. These can be achieved by taking the quaternion groups and adding in a reflection from a dihedral group. This is also not well known, and in fact this term did not exist until December 2021 when I made it up, and it first appeared in the literature in 2024. Next, we'll see the semi-dihedral groups and the semi-abelian groups. These are occasionally tucked away in exercises or examples in an algebra book. And semi-abelian, I don't think you will have heard of that because that's also a term that my student made up in 2021 and first appeared in the literature in 2024. And even though if you Google this, a few other things come up, it's not the same thing as what these things are. So these are lesser known families, but they're really important and they really illustrate concepts better than a lot of the standard groups. Finally, we'll take a tour of 2 broad families of groups at the end of this. First of all, groups of matrices, and pretty much all of these things, if they're finite, can be represented with matrices. And then we'll look at groups that break up as direct products or as semi-direct products. And again, a whole bunch of groups in these families break up that way as well. We'll see a few other visualization techniques and surprises along the way. The focus of Chapter 3 is the structure of groups, and one of the important concepts in there is that of a subgroup. So even though that won't be analyzed directly till Chapter 3, it's helpful to formally define this concept now. And I've mentioned it before. A subgroup of G is just any subset H that is also a group. We denote this with this less than or equal than symbol. Another definition that we'll start using right away is that of the order of a group. It's basically its size. Every group is a set, and a set has a size, and for some reason, in group theory, we call that the order. I don't know why. I don't think it would be confusing at all if we use the word size. Everyone would know what you mean, but because order is so ubiquitous, I'm going to use it as well. Fortunately, we use the same notation that we do for the size of a set and just put this absolute values around it. Finally, the order of an element, little g, is just the size of the group that it generates, or the order of the group that it generates. So this is either the minimal integer k, such that g to the k equals the identity, if this group is finite, or if this group is infinite, when there is no such k, then the order of g is infinite. So again, I think of the order as the minimal such k in my head, with the caveat that if there is no such k, it's infinity. Okay, now for the subject of this lecture, the complex numbers. A lot of you have seen this before, or at least seen most of this, but I think it's important to review it and also to make sure that we are on the same page with notation. So the complex numbers are the set a plus bi, where a and b are real numbers, where I squared is -1. By Euler's identity, e to the I theta is cosine theta plus I sine theta, and that lies in the unit circle. So e to the I theta has real part cosine theta, imaginary part sine theta, and because cosine squared plus sine squared is 1, this lies on the unit circle, and some basic trig tells you that this angle is theta. From this, we get the polar form of a complex number. If we have a number that does not lie in the unit circle, maybe it's out here, maybe this is, call this not theta, but phi, then this number is r e to the I phi. So e to the I phi is just this number on the unit circle right here, and r is literally this radius, which you could write as the tangent of b over a, where b and a are these as before. The norm of a complex number is this r. And some basic trig tells you that this is the square root of a squared plus b squared. I will not derive that here. Again, it's just trigonometry. Here's a remark that many of you already know, but doesn't hurt to see again. If two complex numbers are multiplied together, then their lengths multiply and their angles add. So if z1 equals r1 e to the I theta 1, and z2 equals r2 e to the I theta 2, and their product has norm r1 r2 and angle theta 1 plus theta 2. Here are two examples. If we have complex numbers z1 and z2 at angles theta 1 and theta 2 from the real axis, and we multiply them together, then that's going to be at an angle theta 1 plus theta 2, and the lengths multiply. For this one, I took a number on the unit circle at 45 degrees from the real axis, e to the 2 pi I over 8. And if you multiply that by any complex number, it just rotates that number by 45 degrees. I'm showing this to you because I'm planting in your mind now that numbers on the unit circle can be thought of as rotations. Our first family of groups will be groups of rotations, and I'll show you how to represent them with numbers on the unit circle. Okay, next, let's review the concept of the complex conjugate. This is just the reflection of a complex number across the real axis. So in this case, that's z1. This is going to be z1 bar. And to do that, we just flip the sign. So if this is a plus bi, the complex conjugate is a minus bi. In polar form, r to the ei theta, the complex conjugate is r to the e to the minus I theta, because the angle becomes negative. Note that the norm squared of a complex number, so if we say this is norm r, that's just going to be r squared. So that's equal to r squared. And I claim that this is z times z bar. So z times z bar is r e to the I theta times r e to the negative I theta. Notice that the angles add to get 0, and we just get r squared times e to the 0, which is 1, which is r squared. So this is basically the Pythagorean theorem, because the norm of z is the square root of the norm squared. So the square root of z bar, which is the square root of a plus bi times a minus bi by difference of squares. This is the square root of a squared minus b squared I squared, which is just a squared plus b squared. Next, we come to the all-important roots of unity. This is a very straightforward concept. I don't think it's particularly difficult, but in my experience, it often slips through the cracks, and students may not see it in their undergraduate studies. Now, it certainly would come up in complex analysis. It sometimes comes up in abstract algebra, but it could come up in calculus, but it usually doesn't. It's all about the roots of the polynomial x to the n minus 1. So we know that polynomials of degree n completely factor in the complex numbers, so they have n roots, not necessarily distinct. But I claim that this polynomial will always have n distinct roots, and they lie in the unit circle. And if you see a few small examples, I think it's pretty plain to see how the pattern generalizes. So for n equals 3, there are 3 roots of x cubed minus 1. So we're looking for numbers on the complex plane where x cubed equals 1. So clearly 1 satisfies that, as does e to the 2 pi I over 3, because if you cube this, the angle adds 3 times and you get to here, but also e to the 4 pi I over 3. So if you cube this thing, the angle adds 3 times and you also get a multiple of 360 degrees. I think you see why. Let's go to n equals 4. So x to the 4. So we're looking for complex numbers that satisfy x to the 4 equals 1. Well, 1, negative 1, I, and negative I all satisfy that. You probably know that. But you can see why geometrically, because if you take any of these angles, either 2 pi I over 4, or 2 pi I over 2, or 4 pi I over 4, or 6 pi I over 4, etc., you can see why if you multiply that angle by 4, you will get a multiple of 2 pi. Finally, the roots of x to the 5th minus 1. I think you can see why all 5 of these complex numbers, e to the 2 pi I over 5, and in general, e to the 2k pi I over 5, if you raise them to the 5th power, let me write this as x to the 5th equals 1, you will end up with a complex number of norm 1 whose angle is a multiple of 2 pi. Formally, for an integer n at least 1, the nth roots of unity are just the n roots of x to the n minus 1, and they are of the form zeta n to the k, where zeta n is 2 pi I over n, so this first one, and k is between 0 and n minus 1. Here's one more definition. If n and k are relatively prime, then we say that zeta n to the k is a primitive nth root of unity. So let's think about which ones here are primitive. So what things are relatively prime to 3? Well, that's just 1 and 2. What things are relatively prime to 4? That's 1 and 3. And what things are relatively prime to 5? 1, 2, 3, and 4. And one way to think about what the primitive roots of unity are is these are ones where you need n powers of x to get back to 1 and not fewer than n. So here, this is a primitive second root of unity. You don't need 4 powers to get back to 1. You only need 2. Here, you don't need 3 powers to get back to 1. You only need 1. A quick remark, this is important, the nth roots of unity form a group under multiplication. So these three numbers, the actual complex numbers, form a cyclic group of order 3. These 4 numbers form a cyclic group of order 4, and these 5 form a cyclic group of order 5. I think you see the pattern. We just saw the nth roots of unity for n equals 3, 4, and 5. Let's now see them for n equals 6. And this is going to motivate the theory of what's called cyclotomic polynomials, which is coming up next. So the 6 roots of unity are the roots of x to the 6 minus 1. And since 1 is clearly a root of this, we can factor out x minus 1, and the rest ends up being x to the 5th plus x to the 4th plus x cubed, etc., up to x plus 1. And you can see how this generalizes for any n. Now, it turns out that this second factor actually factors further. Well, since we know that this has 6 distinct roots in the complex numbers, we can factor this completely as x minus e to the 2 pi I over 6, x minus e to the 4 pi I over 6, etc. Here's a polynomial with linear factors where literally the 6 roots of unity are the roots. Now I'm coloring them in a certain way that I'll explain soon. I claim that it should not be obvious, but the red terms multiply together to get x squared minus x plus 1. These blue terms multiply, if you multiply them out, you get x squared plus x plus 1. And this green term, this is just negative 1. So this is x plus 1. And I'm going to call these 4 polynomials phi1 of x, phi2 of x, phi3 of x, phi6 of s. Notice that 1, 2, 3, and 6 are the divisors of 6. Okay, what's going on? Here's a picture. Here are the 6 roots of unity. For each one, I'm going to label them with, for what k are they a primitive kth root of unity. So let's start here. We have to raise this to the 6th power to get back to 1. So if you square it, you get here. If you cube it, you get here. Zeta to the 4th, zeta to the 5th, zeta to the 6th. This is a 6th root of unity. Zeta squared, this is an angle of 120. If you square it, you get down here. If you cube it, you get down here. This is a primitive third root of unity. Zeta cubed, this is negative 1. Negative 1 squared is positive 1. This is a primitive second root of unity. Similarly, zeta to the 4th is a primitive third root of unity. And zeta to the 5th is a primitive 6th root of unity. So here's what I claim. This polynomial here, x squared minus x plus 1, the roots of this are the primitive 6 roots of unity. X squared plus x plus 1, the roots of this are the primitive third roots of unity. X plus 1, the root of this is the primitive second root of unity. And x minus 1, the root of this is the primitive first root of unity. And that's what I have here. I also have them in polar form and in Cartesian form. So this should not be obvious. It's not clear why, if I take the primitive kth roots of unity and take every linear factor where that's a root and multiply them together, that I should get a polynomial with integer coefficients. This is something that we will prove much, much later in the class, probably when we do field theory. I think that's like chapter 10. So right now I'm just going to state it without proof so you can see the patterns. It's a good theory to know before you know how to prove it. In that last example, I introduced the cyclotomic polynomials. And the nth cyclotomic polynomial, phi n of x, I'm going to define as this polynomial. And if you unravel this notation, we see that it says that this is the polynomial where the roots are precisely the primitive nth roots of unity. Remember, primitive nth root of unity occurs when, well, e to the 2 pi I k over n, where k is relatively prime to n. So we're constructing a polynomial where each primitive nth root of unity occurs as a root once. And so here's just another way to say that. Now, it should in no way be clear that this polynomial, if you multiply this out, has integer coefficients. An important fact from number theory is not just that these polynomials have integer coefficients, but each one of them is irreducible, meaning it doesn't factor at all over the integers, that is. And also, x to the n minus 1 is the product of all of these for each positive divisor of n, including n. We saw this with n equals 6, but let's do one more example to make sure that we understand this. So let's take x to the 12 minus 1. This number theory fact, which we're not going to prove, or at least not here, says, we will eventually near the end of the course, that x to the 12 minus 1 is phi 12 of x times phi 6 of x times phi 4 of x times phi 3 of x times phi 2 of x times phi 1 of x. And you can actually look up these polynomials. Just Google cyclotomic polynomial. There's a big list of them. And this polynomial is x to the 4 minus x squared plus 1. And this is a polynomial where the roots are precisely the primitive 12th roots of unity. Now, which powers of zeta here are, or which exponents are relatively prime to 12? 1, 5, 7, and 11. So the roots of this polynomial are these four complex numbers. Now we have phi 6 of x. And the roots of that are x squared minus x plus 1. And we've seen this from the previous slide. That's zeta squared and zeta to the 10th. Phi 4 of x. These are the primitive 4th roots of unity. We also saw this in the previous slide. The root, that's x squared minus plus 1. The roots are I and minus I. Notice these are, of all the 12 roots of unity, these are the two ones that take exactly 4 powers of it to get to 1. These are the ones that take exactly 6 powers to get to 1. So you raise this to the sixth power, squared, cubed, 4th to the 5th to the 6th, you get 1. Phi 3 of x. These are the primitive 3rd roots of unity, which is right zeta to the 4th and zeta to the 8th. We've seen this polynomial before. Then there's phi 2 of x and phi 1 of x. Phi 2 of x, again, is x plus 1. There's exactly one of these whose square is 1. That's not equal to 1. And there's one of these that is equal to 1. So one way to think about this is that of all of the of all the 12th roots of unity, take any of them, this one, this one, this one. They all have to be a primitive dth root of unity for some divisor, which means that they have to be a root of exactly one of these polynomials. Just which one is it? So here I'm writing down the summary of what I just said. And just a remark that the primitive dth roots of unity, I don't have this formula memorized. I have to wrap my head around it every time. But there is a nice formula for them. They are the kth power of zeta. Remember, zeta is 2 pi, or is this first one, 2 pi. So this is equal to e to the 2 pi I over 12. So the primitive dth roots of unity are precisely the kth powers of those, where the GCD of n and k is equal to n over d. Again, I don't have this memorized. I don't think of this. I always have to rederive it. But I think it's just helpful to look at this and say, okay, here are the primitive 12th roots of unity. Here are the primitive 6th roots of unity, primitive 4th roots, and so on. If you think about what you're doing, you're really saying that the GCD of 12 and 3 is is 3, and 12 divided by 3 is 4. This is a primitive fourth root of unity. The roots of unity are convenient for representing rotations, but unfortunately not reflections. For this, we need to work in the setting of matrices. From linear algebra, we know that a 2 by 2 real-valued matrix A represents a linear transformation from R2 to R2. Namely, it inputs a vector x comma y, and it outputs a vector, which is the product of this matrix times that vector, ax plus by and cx plus dy. A reflection across the x-axis, which, well, we can think about as a vertical reflection, a little preview, hint here, is the map that just sends x comma y to x comma negative y. A reflection across the y-axis, which is, think of as a horizontal reflection, is the map sending x comma y to negative x comma y. Let me draw a quick picture of this. So let me call this z, which we can think of as x comma y. Now if you reflect this across the y-axis, I'm using z to think of it as a complex number. Well, let me call this z bar to suggest that this could live in the complex plane. That's going to be x comma negative y. So if you think of this as x plus yi, this is x minus yi. If you reflect this across the y-axis, now you get something that looks like this. So this is, what is this? This is negative x comma y, right? And now if you reflect across both axes, x and then y, this is just negative x and negative y. And I claim that this is a 180 rotation of this original vector. You can see that geometrically. Now what is this? This thing here is just negative z bar. And this thing is just negative z. This is going to come up again. The difference between z, negative z, z bar, and negative z bar. And not just in this lecture. It'll come up when we see those semi-dihedral, semi-abelian, and one more group that I talked about in the very beginning. In matrix form, these two reflections across the x-axis and the y-axis are just given by these matrices: 1, 0, 0, negative 1, negative 1, 0, 0, 1. And if you multiply them in either order, not surprisingly, you get the negative identity matrix, which is the map sending x comma y to negative x comma negative y. You can see that right here. Mathematically, what we've done is created a representation of the Klein 4 group, that is the symmetries of the rectangle, by 2 by 2 matrices. That's what a representation is. It's a way to basically represent the group with matrices. So this is like the identity element. This is the vertical reflection. This is a horizontal reflection, and this is a 180 rotation. Now that we talked about reflections in the complex plane, or R2, by matrices, let's talk about rotations by matrices. If theta is an angle between 0 and 2 pi, then the following so-called rotation matrix, cosine theta, negative sine theta, cosine theta, is a counterclockwise rotation of R2 about the origin by theta. And by that I mean, if you multiply this matrix by, let me draw a picture, you have a vector here, z, and you multiply this by a, which are supposed to be the same length, that just rotates z by a. If you rotate by theta 1 and then by theta 2, The result is a rotation by theta 1 plus theta 2. Algebraically, the product of the rotation matrices of theta 1 and theta 2 is the rotation matrix of theta 1 plus theta 2. I'll let you check this if you want to, but I don't think it's really necessary. Just a basic algebraic fact. Recall that multiplication by a root of unity, e to the 2 pi I over n, is a counterclockwise rotation of 2 pi over n radians in the complex plane. In terms of matrices, this is just multiplication by the matrix cosine 2 pi over n, negative sine of 2 pi over n, sine of 2 pi over n, cosine of 2 pi over n. Basically, this rotation matrix where you plug in 2 pi over n. We can also represent rotations with 2 by 2 complex matrices as follows. We take a diagonal matrix and put zeta n, that is the nth root of unity, in the 1, 1 spot, and zeta n bar in the 2, 2 spot. And notice that this matrix satisfies r n to the n equals the identity. So it has order n, just like an n-fold rotation. That doesn't mean that it represents a rotation. There's a lot of matrices that have this property. And we can't really visualize well, or I can anyways, why this is a rotation, because it's a linear map from C2 to C2. And that's a 4-dimensional real values, or over R, that these are 4-dimensional spaces, so I can't really visualize this. But I will say that this matrix, the reason why this bar has to go here, because you could remove the bar and it would still satisfy this. You could put a negative sign in front of here, it would satisfy this. Or you could remove the bar and put a negative sign in front of here, and it would satisfy this. At least for even n, this would. Actually, for odd n, not all of those would work. So maybe that's one reason. But basically, the reason why we need this complex conjugate here boils down to the same reason why the norm squared of z is z times z bar and not z squared. Z bar is always going to be a non-negative real number, whereas z squared isn't necessarily going to be. And that's important. We will see this again when we study the dihedral groups in a couple of lectures, and then we'll see it again and all the variants that I talked about when we see the semi-dihedral and semi-abelian groups that I talked about in the beginning of this lecture later in this chapter. So that's kind of a hint. That's how these groups are all related, really, by this entry down here. And so I think you'll really like that. It's very pleasing once we get to there. And there's also going to be a very pleasing way to represent or to visualize these with Cayley graphs. And without that, you just get these complicated presentations that are unmotivated, which is why they don't really exist in most classes and books. Okay, so a lot of fun stuff coming up. Stay with us.